Hi, let's look at some examples of adjunctions, because otherwise the concept might be a little bit too abstract to really grasp. So I like the category of preorders as a mysterious but not too mysterious category. And I like the category of sets as something I fool myself I understand. So let's see if we can find some adjunctions between these two categories. So the way we usually do this is you have some functor which is kind of obvious, and then you're asking, wouldn't it be interesting if this had an adjoint? So here I think I can think of one obvious category or functor, sorry, which goes from preorders to sets. So if I have a preorder here, so remember a preorder is a set together with an order relation, which is reflexive and transitive. Then I can just forget about the fact that I had an order, right? And that gives me a set. So I could just map this to the underlying set of the thing. And similarly, if I have another one and morphism between them, there was an F plus a proof that it was order preserving, right? So here I can just forget about the fact that my function was order preserving, and that will give me a function between the underlying sets. Right, so map that to that, and already map that to that. So that should give me a functor, and then I have to check that it preserves identities, etc. But that's good to work out, I think. So this is called the forgetful functor from this category of structure to this category with less structure, right? So I'm forgetting some of the structure. So now we could ask, what would it take for this functor to have an adjoint? So let's see if we can find a right adjoint for it to make it a left adjoint. So that would mean that functions from forget x less than into b should be the same thing as order preserving maps from x less than into something of b, right? So we're trying to find this something. Okay, so what is this? Well, this is just x. So here at the top, we just have functions from x to b. We want them to be the same thing as order preserving maps from this order into whatever we make this, right? Well, first of all, we better make this thing here have at least the same underlying set, right? Or something related to it, because otherwise we couldn't use this function. So I think we have to do that. And then we have to say what the order is. And the only way to preserve all possible orders over here is probably to make everything here related, right? Because otherwise we can't do it all the time. And remember, we can't make this depend on whatever morphism we have up here or anything like this. It has to work for every morphism, right? So I think if I make this always related, then that might work. So this is sometimes called the chaotic order. So saying that chaotic of the set B is the same underlying set, and then B and B prime are always related, right? It's chaotic because everything is related to everything else. And now the claim is that this is going to give us a functor going the other way, and that we're hoping that forget is the left adjoint of chaotic. So let's see if we can do this in Agda. So here I've already defined the forgetful functor. So it's from preorder to set. On preorder x, we just take the carrier as our set. And on a monotone map, we just take the underlying function. And then it's really easy to show that this preserves identities and composition, right? Okay, so now let's see if we can define this chaotic functor which goes the other way. So it takes a set and it makes a preorder where we want the relation to be chaotic. So let's see. So we have to say what we do on objects. So we get given a set B and we have to make a preorder. So that means we have to give a carrier and an order relation and prove that it's reflexive and transitive and propositional. Right. So the carrier we said should be the same thing as B. And the order relation we wanted to be this thing where everything was always related. So if I have a B and a B prime, then top is something I can always prove, right? Okay, and then here I have to show that this is reflexive. So every x is related to itself. But this is really easy because everything is related to everything else. So I can just give TT, which is the element of the unit type, right? And here I have to show that it's transitive. So if A is related to B and B is related to C, then A should be related to C. Well, that's easy because everything is related. So here's I don't care, and return TT. And similarly here, I have to show that if I have two proofs in the unit type, then they are equal. But the unit type is the type with exactly one element. So this should just be true, P and Q. And they are equal because there's exactly one element. So they must both be that element. Right. Okay, here I'm given some f, which is a function from A to B. And I have to make a monotone map from this chaotic preorder at A to the chaotic preorder at B. Right. So yes, I have to give an underlying function. We should go from A to B. Well, I should clearly use the f I've been given. And I have to show that this is order preserving. So if I have an x and a y in a proof that they are related, I have to show that their outputs are related. But that's really easy because everything is related. Okay, and now finally I have to show that this preserves identities and composition. And here, this is not so easy to see maybe. What should we do? Well, we should remember that if we are trying to prove an equation between preorder morphisms, then we have this EQ monotone map. Which says that it's enough to show that they're equal on the underlying functions. So that's going to make it easier because now the underlying functions on both sides are just the identity function. So it's provable by REFL. And similarly here, for preserving composition, we can do this. And then we have to see if these compositions are the same, but the underlying functions are again exactly the same. So that's just REFL. Okay, so we have a functor. Now we need to show that this is an adjunction. So let's see what we have to do. We have to give to and from maps, show that they are inverses, and that this is natural. So the to map is the thing that takes us here from the top to the bottom, right? This is 2, and from is the map that takes us from the bottom to the top. And then we have to show that if I start at the top, go down and then up again, then I end up at the same place. And similarly, if I start at the bottom, go up and down again, I end up at the same place. So we have to be inverses. Right. Okay, so let's see if we can do this. So here's 2 from top to bottom. So I get given some h. Let's see what happened here. I pasted something in which I shouldn't have. Here I get given some h, which is a set function from the forget of x to b. And I have to make a preordered morphism, so a monotone map from x to the chaotic thing at b. Right. Okay, so that means I have to give an underlying function and the proof that it's monotone. So for the underlying function, I made sure I have exactly what I wanted, because I had a choice of making this b or something else, right? And I made my life easy for myself. And now I have to show that it's monotone. So if I have x and a y and a proof that they are related, to show that the results are related. But that's by design really easy, right? Everything is related. That's exactly why we choose this definition, so that I can make this upgrade of a function to an order preserving relation with this very special order, right? Okay, and going the other way, if I have some k like this, okay, so I have a monotone map from x to this chaotic thing, and I want something from the carrier of x to b. Well, if I look at the underlying map of k, that's exactly what I have, so I'm just going to use that, right? So now I'm again basically forgetting about this useless order preservation proof. Okay, and now I have to check that this is inverses. So if I start in h, so I start with just a function, and then I make it into an order preserving thing, and then take the underlying map. Then because I use the same h as the underlying function here, I'm just going to get the same thing back again. Right? So that's always referable. And similarly, if I start with a k, so I start with a k, I look at its underlying map, and then I upgrade it again to an order preserving function like this, then it looks like I could be in trouble because I've now thrown away the preservation proof I originally had and replaced it with this, right? But remember, we had this principle that it's enough that the underlying maps are the same. The underlying map is k in both cases, right? So that's also okay. And finally, we have to show that this is natural. So it doesn't matter if we first go across and then compose, or if we first compose and then go across, right? So let's see what we have to prove here. We're given an f and a g to compose with. Okay, and we have to show that this is first going across and then composing, I think, and this is the other way around. Well, so it's proving equality of two functions in set, right? So we can do that with function extensionality. And now we are proving an equation between two preorder maps. So we can use EQ monotone map. And now we see that we've been lucky. This is exactly the same. So we can just prove this with REFL. Okay, and this happens quite a lot, that you have to be creative when you come up with the functor. That's the hardest bit. Then you have to do some thinking to define the to and from functions so that you can actually prove the inverses. But most of the time, to prove that it's natural is completely mechanical and not a problem if everything else is right. It's very unlikely that you got all of this right, but it wasn't natural. So it makes sense to focus on these bits and the functor and just do this. It's an afterthought, more or less.